Hello and welcome back, everybody. Moving on to section 6.3. You can probably feel it. The book's almost over. This is the last section of the book. We're going to go through 2 more videos, actually. This is called Galerkin methods. And this really is probably the most common method of approximating PDEs in the 21st century. You maybe have heard of finite element methods, not to be confused with finite difference methods, but finite element, not the word difference. Finite element methods are a version of these. And in fact, Galerkin methods is kind of too broad of a name to say that there's a specific one, but the overall intuition of a Galerkin method is always the same. And finite element methods are a version of those. And really they're preferred over finite difference methods for a few reasons. So finite difference methods are grid spacing. We kind of saw this. It could poorly align with the original boundary. For example, suppose I choose a grid that looks like this. And I know this is like a very arbitrary choice that I'm making here, but suppose there's my grid, and for some really weird reason, suppose this is my domain. Like, how sad would it be that this is my domain, and I've got a grid there, and it only has one entry on the inside? So, like, that would be unfortunate. It obviously doesn't occur that often, but you never know. You never know that your domain might poorly align with the grid spacing you've chosen. You also have to picture, this whole approximating the derivative with plus or minuses. You really have to have a good picture of what's going on to make sure that you're always headed, from a boundary into the domain, making your choices correctly. And when the equations are nonlinear, the system which is constructed from your finite difference methods may be ill-defined. Now, this is going to be true in Galerkin methods as well, so we can't necessarily sidestep this issue. But in finite difference methods, definitely you had maybe ill-defined solutions. And finally, there's this idea of methods being called unstable. And we didn't really talk about this, but what unstable means is that as you increase the size of your domain, there's a positive feedback effect that can increase error, right? So it's like if you're moving your approximations to the right over time, you may have a good approximation here, but then if you go way to the right, it may be just terrible. And so basically, because error terms can propagate. Once you have a little bit of error in one section, it propagates to the next section. This is because of kind of the local nature of finite difference methods. In Galerkin methods, because everything is we're going to find out it's defined on the whole space kind of all at once. Your error may be worse in some sections, but at least it's kind of like equal over the entire space. It's not like going to become exponentially large as you increase the size of the domain. So we're kind of going to sidestep, and actually even in this third case, you do maybe have ill-defined equations there, but you can kind of, in Galerkin methods, find the best approximate solution to a system of equations, even though the system itself may not have any equations. This is like, for example, the function, when the function x squared plus 1 equals 0 has no solutions, right, because it looks like this. In R, at least, the best approximate solution would be that one, because it's like the closest to 0. And so you have this notion of being close to a solution with Galerkin methods, and it actually makes sense to use that idea. So what is the actual idea? What are we trying to do? I'm going to start down here to describe it, but I will refer up to that language in a bit as well. So let's just consider a PDE, and this is the way we'll consider our PDE. Its solution phi that we're looking for probably exists in an infinite dimensional vector space, right? It's kind of the idea of a domain of an operator. It's an infinite dimensional vector space. And so it probably has this representation. It's a representation of phi in an infinite dimensional space. So it's got this representation in infinite dimensional space with infinitely many basis functions. Galerkin methods say, maybe I don't know what phi is, but maybe for some reason I have an intuition on these basis functions. This intuition often comes from the spectral theory. If you have a collection of orthonormal eigenfunctions to an operator, that's really going to be a good collection for a basis with which to represent a solution in. So maybe you have a really good intuition on the basis that will produce phi, or you could represent phi in. And then it says, what if I take this j here, we're going to make a finite set. So Galerkin basically says, let's reduce, instead of some infinite set, the reason I haven't really quantified over j there, but the capital J below, I'm saying let's quantify over a finite set instead. And when we give ourselves only finitely many basis elements, we don't necessarily know that that's going to give you phi, but it should give you an approximation to phi. Because what does it mean to represent something with infinite? It means the limit of finite. This is literally how mathematicians have defined, infinite sums is as the limit of finite sums, which means a very large number of finite sums has to be really close to the actual solution. So we're going to restrict ourselves to some finite set of basis functions instead of infinitely many basis functions. And what that's going to do is if I grab finitely many of these, and I say, okay, phi is approximately finitely many, but let's replace each phi with its approximation by finitely many basis elements. What I can do is find the quote-unquote best possible phi in the finite set to solve the PDE. But it doesn't solve the PDE. It's going to approximately solve the PDE, right? So best possible means what is kind of the best approximate solution to this PDE. It's going to be basically minimizing this equal sign says equals 0, right? And so best possible in some ways means closest to 0 for that right hand side. There's definitely going to be at least one element in this space that's closest to 0, and that must be a fairly good approximation to the PDE itself. Of course, as you increase the number of basis functions to infinity, if phi was in that space originally, of course it's going to be fully reconstructed. So that's the Galerkin method, kind of the intuition behind it. I will mention though, the way I've set it up here, these boundaries can really get in your way. If I'm only looking at the best possible approximation to that 0, best in the sense of close to 0, then this equality has all of a sudden become meaningless. So that makes your life kind of hard. So what we like to do with the Galerkin method is actually force each of these GKs to be equal to 0. Why does that work out well? Because if these bases are all 0 on the boundary, then a sum of finitely many bases will give phi being 0 on the boundary. Which means if our original PDE had a 0 on the boundary instead of a G, as long as the basis elements can have a 0 on the boundary, then we know that this is always met. We know the boundary conditions are always going to be met, which means our best possible can truly be restricted to just that equal sign. So we want to know how to play those games. The way we play those games is something I call boundary zeroing. I don't know if there's actually a definition and name for this out in the world. It's used all the time. I don't really think it has a name. So I'm going to give it a name, calling it boundary zeroing. Makes a lot of sense. What we do is we can somehow force the boundary to be 0. How do we do that? A boundary zeroing of the PDE consists of, first, a smooth function phi on the domain of the PDE, for which I'm already satisfying the boundary conditions. Okay, so phi satisfies boundary conditions, but doesn't care about the PDE itself. Right, so phi is only going to be looking at this, and it says, hey, I've completely forgotten about the PDE itself. But if I can find a function that satisfies that, you basically have, in step 2, you have this pairing of something that only satisfies the boundary. In step 2, you end up with something that only satisfies the PDE itself, right? There's the PDE itself, and the boundary value is 0. So we call this modified PDE the boundary zeroed PDE, where I've replaced G with a 0, and then that top PDE is really a modification of the original PDE. You'll notice what have I done is I've replaced every phi version of phi with psi plus phi. It's the second phi being from step 1. And so you kind of have a modified PDE in the boundary zeroed case. And so this is going to be a PDE in the unknown psi alone, because we actually already know what this phi is equal to. So basically what it means, right, so the full boundary zeroing process is that after we solve both 1 and 2, the original phi solution is just going to be the sum of 1 and 2. Although my orders are backwards there. But if you just add the solutions to 1 and 2 together, you can find the original solution. So what we want to think about then is that Galerkin methods can solve these for us. They solve 2. This part 1 is up to us to figure out on our own. But it's usually not too difficult to find something that satisfies the boundary conditions, not the PD itself. So let's see an example of this in action. That was technically a proposition, so I do have a proof there. Let's actually see an example of this. This isn't even getting into Galerkin methods at all. I'm just showing you maybe how boundary zeroing can be useful. So let's find a Fourier solution. This is really going to be a Fourier sine series solution to Laplace's equation with boundary zeroing. Let's suppose that we want to solve this PDE. That's Laplace's equation, and I've got some non-trivial boundaries going on. where I'm saying in the x directions, I want to be equal to cosine x over 2 and negative cosine x over 2. This is when y reaches the endpoints pi or negative pi. And so this is the Laplace equation on the square, where when y is pi, x is negative cosine x over 2, and when y is negative pi, x is positive cosine x over 2. And thankfully the boundary is already 0 everywhere else. But what is Laplace's equation? It's going to construct the soap film, right? Kind of the soap film in between those places. So we're going to get some nice little, we want some nice little interpolation between all of this for us. But the Fourier solutions are really any sort of spectral method, of which the Fourier method is one of them. Any sort of spectral method can't really handle non-zero boundary conditions. And so what we need to do is we need to boundary zero this by basically finding, in step 1, a function that meets these qualities. We don't care about the PD itself, but we need to meet those qualities. Now, by inspection, I realize that's a little bit annoying. Why would you say by inspection? Well, it's not that hard. All I'm doing is I'm saying, hey, both terms have a cosine in them, so definitely both should have cosine in them. Now, what do I need? I need a function of y that's equal to negative 1 at negative pi. I need a function of y that's equal to 1 at pi, and then I'll add a negative sign in to, account for that negative sign. So, what is a function that's equal to negative 1 at negative pi and positive 1 at pi? Everybody's favorite is sine y over 2. So that's where sine y over 2 showed up. I could have actually chosen quite a few others. There's nothing special about me choosing sine y over 2. You could choose whatever you want. This is still going to work out as long as it's smooth. But I found out that sine y over 2 definitely meets those boundary conditions. So that's step 1 of the boundary zeroing, right? To go up here, step 1 just needs to be in some function that satisfies the boundary conditions themselves. I found that function here. Then in step 2, what I do is I grab the original PDE and I replace the phi in there with this psi plus phi, where the other phi was from step 1. Okay, so that's from step 1. I don't actually know what psi is. Okay, but phi from step 1, we know what that is. So I'm going to replace that phi with negative cosine x over 2 and sine y over 2. By the way, the boundary zeroed PDE in step 2 definitely has 0 everywhere on the boundary. It's kind of the whole point. It means my Fourier methods are going to work for this. But I do have to calculate this delta of phi explicitly. There it is. So that I can actually realize what this PDE is trying to tell me. This PDE is trying to tell me that phi, right, delta of phi actually takes this value. And I've moved it to the right-hand side. So what I'm doing is I've basically translated Laplace's equation with non-zero boundary into Poisson's, which you'll recall was just the inhomogeneous Laplace's equation, into Poisson's with zero boundary. So I'm paying the price of being inhomogeneous now. But that's not too bad, because when I'm inhomogeneous, spectral methods are fine for that. It's kind of the bread and butter of Green's functions, right? Is homogeneous equations. And so we just use spectral methods, theorem 5.5.10, proposition 5.5.13, to say that my solution is literally just the right-hand side, the inhomogeneous term, against the Green's function. And I find the Green's function by finding the eigenvalues of this operator on that domain. In this case, they end up being sines and cosines. So yeah, Green's function is not too pretty. It's huge because there's a lot of eigenvalues, eigenfunctions here. But you find the Green's function, you construct it, and then you compute, what is that? This kind of integral, right? It's just an integral transform of the inhomogeneous condition. What is that actually equal to? If you solve it out, you find out what it's equal to. It's equal to this term. Now I should mention it's not actually equal to exactly that term, because what have I done here is, in step 2 I've solved the inhomogeneous PDE with zero boundary. The actual PDE that I'm trying to find was the original one with the non-zero boundary, and so you take the inhomogeneous solution, which is the Green's function solution, and you add your original function. That was the negative cosine sine function, right? And so you add that function onto the end, and then you get your true solution to the original PDE. And so this is the solution to original PDE via boundary zeroing. And what do you know? That looks exactly like what you thought. There's my y direction of height 0. Here's my x direction of height cosine x over 2, and then my other x direction of height negative cosine x over 2. And then the soap film interpolation of all of that. So that's not really the point of this section. The point of that part was just to say Galerkin methods can solve zero value boundary conditions, which was the same kind of with this whole spectral theory at the end as well. But Galerkin's going to be able to solve that for me. It's not going to be able to solve arbitrary boundary conditions for me. So we're always going to want to go through some boundary zeroing if we're going to use Galerkin methods. But basically from this point onwards, when I define Galerkin methods, I'm going to go ahead and define that all of my basis functions equal 0 on the boundary. This is something you have to keep in mind with Galerkin. Make sure the basis functions equal 0 on the boundary. You can always get there using some boundary zeroing. So what I actually start with, you're like, wait a minute, the definition of this is not a Galerkin method. Very sorry about that. The definition is kind of a Galerkin method. I'm calling it the name method of mean-weighted residuals. This is well defined in the mathematical literature. If you look up the method of mean-weighted residuals, like some people just call it MWR, MMWR. It is kind of even a broader perspective than Galerkin methods, but it's also like the right method to think of while we're here. So what is going to happen in this method of mean-weighted residuals is I'm going to start with a PDE with 0 boundary values. And you'll notice that's number 1 important, but number 2 achievable because of my boundary zeroing. So we've got a 0 there for all of the boundary values on my PDE. What we do for the method of mean-weighted residuals, very easy to say, so we're going to find a set of finitely many linearly independent functions. This is going to be our basis. And then I have some quotations here. I say naturally adapted to the PDE. Okay, what does that mean? And then obtaining the value 0 on the boundary. What does it mean to be naturally adapted to this PDE? Got a footnote there. Say indeed, it's incredibly vague. Very sorry about that. But what this usually means is that the functions are eigenfunctions of the PDE operator with boundary value 0. This goes back to chapter 5 when we were, verifying something was Hermitian and then could find some eigenfunctions that we knew were orthonormal. It's kind of a super cool thing. So this is why chapter 5 is very important, even in applied math. You can find these sort of sets of functions very easily if you find these orthonormal sets of eigenfunctions. So that's usually what you're going to choose, but it is vague, and you'll either just decide on a collection of these functions that you like, and then you use it for every PDE you ever use it for. That's kind of what finite element methods are. Or you're going to try to find a very specific set. We can't get into all of that here. It's what you take a numerical methods course for. Anyway, once you have this set of finitely many functions that you feel like maybe are a good choice for this PDE, you're going to construct the finite sum approximation, which I'm calling phi tilde sub j because that's kind of this index set that my finitely many functions are indexed over. And really what we don't know here is these CJs, right? This is what we don't know. And so the collection of CJs is going to be what we're going to look to solve for. So what we want to do, basically, once we have this, is use the PDE itself to give us absolute value of j equations, and the CJs are our unknowns, hence can find them. That's what we want to do, but the question becomes, what does it mean for that PDE to give us j equations? So that's where we're headed with the rest of these method of mean-weighted residuals, is how do we use the PDE, which I've just restated in step 3, but now with our phi tilde sub j. How do we use that PDE evaluated on those finite sums to give us, the size of j possible equations that we can actually solve for all the CKs with? Well, the way we do that is we define something called a weighted residual. A weighted residual is really a function of the coefficients. Function of the unknown coefficients. Function of the unknown coefficients, and it's going to be defined as an integral of f, now f's the left-hand side here, the integral of f, the left-hand side, against something called wk. Those are called weight functions. And there's going to be k of them, right? So k, and here I'm saying for k in j. And so because k is in j, there are just as many, or equally as many, weighted residuals as there are unknowns. And this is really what's going to make our lives easy. We have an equal number of weighted residuals as we have unknowns. In the next step 5, before I get there, in the next step 5, you'll notice that the weighted residuals are set equal to 0. And I want to mention why they should be set equal to 0. We set this expression equal to 0 because we want f to be equal to 0. right? You can imagine if f were truly equal to 0, it may not be able to achieve the value 0. But if f were equal to 0, then this f right here is equal to 0, which means what is the value of that integral? You're integrating against 0. The value of the integral is 0. So that's where everything kind of lines up, is you're comparing this 0 to this integral to then this 0. And because you have a bunch of zeros sitting around, you get a good approximation. Now the idea is that in some cases, this integral won't be 0. This is where the weights play an important role. In choosing a, I'll put this in quotes again, natural choice of weights, we have J equations equal to 0, but maybe f is not equal to 0, right? The approximation is saying f's probably not equal to 0. We would love it if it were equal to 0, but we're going to choose k weights and then use that to construct our system so that at the very least, against these weights, it's 0. Put it in quotes, f is 0. So f kind of behaves like 0 in some abstract sense of against these particular weights. It doesn't necessarily behave as 0 always, but it, some set of weights. Now, we haven't defined weights yet. What in the world are weights? That's kind of why this method is broader than the Galerkin method. You can choose any collection of weights. There are like natural choices for weights that make the method useful, and the Galerkin method is one of those choices of weights. But for now, honestly, in this definition, the weights are just treated left as whatever function they have to be, whatever function you want them to be. Anyway, having constructed these weighted residuals and having set them equal to 0, this will be a system of the same number of equations as we have unknowns, and hence it will be invertible. We hope so. Right, nonlinear situations, you may not get that again, but you would expect in a lot of cases this is an invertible system, and so you can solve for the coefficients Cj. I've given an extra subscript there to say Cj sol for being, these are the solved versions of them. You then just decide, hey, if from the beginning I said that the approximation were just the Cj's against the Ej's, all I do with the Galerkin method is say, now that I've solved for a collection of Cj's, I'm going to put them in my approximation. And so you get this approximation where, at the very least, f, the solution, behaves like 0 against a specific collection of weights. That's really what's going on in weighted residuals. I'm now going to go into the Galerkin method that actually works. The Galerkin method is the version where our weights are exactly the basis functions themselves. So in the Galerkin method, weights are basis functions. So you're given your basis functions, you're constructing your solutions against them, but you're also using those as the weights. And this is a very natural choice because it means as you extend the dimension to infinity, what you're doing is you're using all of your full basis functions, which means you're spanning the entire space. And then if you're saying I'm equal to 0, right? If you're setting the residuals equal to 0 against every single basis function in the space, that's what it means to be actually exactly equal to 0 in a space. And so this is why the Galerkin method feels very natural. It's saying, hey, I'm going to let the weights, the collection of functions I want to be 0 against, be exactly the basis functions. In the event I have infinitely many of them, I'm 0 against infinitely many things. It makes me 0 everywhere. So the Galerkin method is kind of that specific case of these, and that's what you want to think. You just want to think, hey, if I would rather replace this with the Galerkin method, I'm just going to replace this with my E, my basis element, and then proceed from there, and you'll get your Galerkin method. But I do want to remark, as kind of this last remark here, that there are two other very common weight functions. You can actually use weight functions being delta functions for some collection of points in your domain. It's almost like in the finite difference method, you have this lattice structure in your domain where there's only finitely many elements in there. You can do that kind of the same thing where you lattice out your domain and then set out your weight functions to be the delta function at those points. And what this does is it verifies that this function f, which you're trying to solve, always equal to 0, you let it be equal to 0 at this finite collection of points. It's like I'm forcing the solution to obtain the value 0 at so many points under the PDE. And as the number of points tends to infinity, you're filling out all of omega because omega is bounded, and so you only have infinitely many points in a finite space. You're going to be equal to 0 everywhere. So that's a very common method as well. It's called the collocation method. And then there's also a system where you use actually the partial derivative of f in the ck direction. Now this feels a little bit weird. What's actually going on there is a Lagrange multiplier optimization. So you're really starting with kind of this expression, and you're saying Lagrange multiplier optimization gives kind of the integral of f against its derivative in the k direction. And then you have, k of these, or capital J of these. That is what the Lagrange multiplier would be in that situation. And so what you end up doing is you either minimize or maximize this quantity. And you'll notice that quantity, this is capital F still, right? Capital F is, if you go back to the PD itself, capital F is the term that you want to be equal to 0. Well, if you minimize this quantity of capital F, if you manage to get this to be as close to 0 as possible in the space, then you've basically approximated your PDE because you force that term to be as close to 0 as possible. Now that's as close to 0 kind of in some volume sense, but that's the idea with this other method of weights, which is called the least squares method. And of course that's because you're performing the square of the function and you're going to try to minimize it. So it's the least squares method of mean weighted residuals as well. So we don't get into either the collocation or mean square or least squares here. That's just because we don't have time. So we're going to do 2 rounds of Galerkin. I will save those 2 rounds of Galerkin into the next video though. So I'm going to stop here for now. We can talk about it in class. See you then. Bye.